So now that we've talked about Java completable futures and I've explained how its capabilities map onto the reactive programming paradigm, let's kind of take a step back and talk more generally about synchrony and synchronous programming versus asynchrony and asynchronous programming. And we'll talk about the pros and cons of each approach. So method calls in your typical Java programs, most likely almost everything you've written up to this point, are largely synchronous. And some examples of this, of course, would be if you make method calls on Java collections like hash map or array list or tree set, as well as different behaviors in Java's streams, including parallel streams for the aggregate operations. Those are all synchronous calls. And what that means is that the callee, which is the thread or the method that's called by a caller, will borrow the thread of the caller until its computations are done. So you can kind of see here a little animation of what's going on, where we're going to have a caller look for some word in some input, and we get a result back. And notice how the call blocks until we get a result back from the callee. So the caller blocks until the callee is done with the computation. And this is often called request response as a model. It's a request response nature of these two-way calls. You invoke an operation with 0 or more parameters, you get a result back. Then you invoke the next operation with 0 or more parameters, and you wait until you get the call back. So that's kind of how things look visually. So let's talk about the good things about this. So there are some benefits of synchronous programming. First of all, it's very intuitive because we've done it for a long time. That's typically the way we write code. So it's intuitive to program, and it's relatively intuitive to debug. And that's because it maps very cleanly onto these common two-way method patterns. You can take a look at the link at the bottom of the page, which talks about essentially two-way method call patterns as a pattern. Another nice thing about this model is that local state from the caller, the method that's making a call, is automatically saved and then restored when the callee returns. And that's because the implementations of these things typically use stacks of activation records, and the activation record keeps track of the local state. So let's take a look at a very simple example just to make this clear. So here's a method called download content, where you're going to give it a URL, and then it's going to go ahead and give you back an array of bytes corresponding to the contents of that URL. And you can see here what it does is it goes ahead and it allocates a new array called buff, which is a byte array of buff size bytes. And that's a local variable that's stored in the activation record. And then we go ahead and we open up a new byte array output stream called OS. Then we open up an input stream called IS. Those things are also local variables stored in the activation record. And then we go into a loop. We define a loop counter called bytes, which keeps track of the number of bytes we've received. And then we use IS, which is the input stream, to read a buffer of bytes into the buff. And then we go ahead and write those bytes from buff to the output stream. And you'll notice every time read is called and every time write is called, when those calls return, the local variables like bytes and buff and so on, and IS and OS, all retain their state and their meaning and their values when the call comes back. So that's all wonderful and nice and magically clean and very, very intuitive, very easy to program. We've done this kind of code a gazillion times. That's the most common way you learn to write code. However, as I always like to say, it's not all unicorns and rainbows, so there are also some cons or some downsides with synchrony. One of the main problems is it doesn't necessarily leverage all the parallelism that's available in modern multi-core systems. And so if you take a look at this link, which I, as usual, have to fix, I'll fix it in the slides that I put out there, you see that under the hood, these calls that are being made with synchrony will block the calling thread. And blocking threads, especially if you have a bunch of blocking threads, can lead to some problems because you end up with additional synchronization costs, additional context switching costs, additional data movement costs, some additional memory management costs, and so on and so forth. So you end up having to spend extra time trying to coordinate the different threads and their sharing of the information. So it just basically gets in the way, is the best way to put it. Another challenge is trying to figure out how to select the right number of threads. Now, we've talked about this earlier when we were talking about how the fork join pool, the common fork join pool, is used in the context of Java parallel streams. And if you recall, in that discussion, I talked about the fact that you had to be very careful how these things were designed so you wouldn't either underutilize or overutilize the available resources. So let's take a look at a very simple example. This is an example that uses a parallel stream to download a bunch of images from some remote websites and then apply various filters to transform the images, which should sound quite much like your programming assignment. So if you do the parallel streams version, one of the tricky issues here is how many threads should you have in your pool? If you have a lot of threads, then you can make things run faster, but you'll end up potentially using a lot more resources. Conversely, if you have a very few number of threads, you can have more efficient resource utilization, but your program may run slower. So trying to figure out the right number of threads is tricky, especially for I/O-bound operations that really need to use more threads in order to run most efficiently. So as a consequence, you may need to play some tricks to change the size of the common fork join pool. And we kind of talked about how you could do that. There's a couple different ways you could do it. You could either set a system property, like we're showing here, where you set the desired threads, but that is kind of hard because it's hard to know how many you need ahead of time. And it also has this ripple effect. Or you could use the manage blocker mechanism to temporarily and automatically increase the size of the common fork join pool. The downside there is that you can only use this technique with the common fork join pool, so you're kind of locked into that approach. And it may also grow too big if you're not careful. So there's pros and cons of synchronous programming. And not surprisingly, what we're about to talk about is how the completable futures framework helps to overcome the cons with Synchrony.